The stereochemistry of the Diels-Alder reaction is one of the more complicated parts of the Diels-Alder chapter. Stay tuned where I give you some pro tips to be a Diels-Alder ninja. While the mechanism of the Diels-Alder reaction is one of the simpler mechanisms in organic chemistry, the stereochemical outcome is one of the more complicated stereochemistries in organic chemistry. The mechanism for the Diels-Alder reaction is fairly straightforward. The diene bonds with the dienophile bonds with the diene, and the double bond moves to the central position. I'm using bouncing arrow notation here. If you're not familiar with bouncing arrow notation, check out my video linked down below. Drawing the skeleton of the product is also fairly straightforward. As long as we number the 4 carbons of the diene and the 2 carbons of the dienophile the same way every time, then the cyclohexene reaction will always form a cyclohexene product. And if we always number it the same way, then the rest is just decoration. This isn't a video about the mechanism of the Diels-Alder reaction or drawing the skeleton of the product, but I have a separate video to that one linked down below. The challenging part of the Diels-Alder reaction is figuring out the stereochemistry of this product. There are 4 stereocenters in this product. That means there are 16 possible stereoisomers that could form, but amazingly, we only form 2. One product and it's enantiomer. Let me show you how. Before we dive into this Ninja Level 5 problem, let's take a step back and look at some simpler examples to build up our stereochemical understanding of this reaction. The first thing to understand about the Diels-Alder and its stereochemistry is how these molecules are actually oriented in 3D space during the reaction, because it might not be what you think. It looks like these 2 molecules just kind of approach each other side to side and they click together to form the Diels-Alder product. But that's in fact not how it happens. In fact, they approach each other top to bottom, one molecule on top, one molecule on bottom. That is important for figuring out the stereochemistry for this reaction. In fact, for stereochemistry for the Diels-Alder reaction, I'm going to recommend that you redraw these in a 3-dimensional perspective drawing so that you kind of flip them on their sides so that they are sticking in and out of the plane of the paper. Let me show you. We'll start by drawing the diene kind of in a perspective drawing so it's coming in and out of the plane of the paper. I like to draw a bounding box. That kind of helps me see that this is a new perspective drawing for this molecule and that the diene is coming in and out of the plane of the screen. Now, the dienophile could either approach from the top or from the bottom. By convention, we have the dienophile approach from the bottom. I don't know why, but that's just our convention. And I put a little bounding box here as well to show that this is coming in from the bottom, approaching the diene. If we can see the orientation of this molecule, then we can look at the bonds being formed. We're forming a bond between this carbon and this carbon, and this carbon and this carbon. These are the new bonds being formed. Next, I'm going to draw a perspective drawing of the product in the instant after the bonds are formed. It won't be in the flat cyclohexene shape we know. It'll still be in this puckered shape. Let me show you. In that instant after the bonds are formed, the cyclohexene is still in this puckered shape. What happens next is we unfold this bottom part to bring it back into planarity, to bring it back to the cyclohexene we know and love. And that unfolding is going to be a key step in figuring out the stereochemistry for this reaction. So before we can go any further investigating the stereochemistry of the Diels-Alder reaction, we have to understand these 2 principles. First, the molecules approach each other top to bottom, not side to side. And by convention, the diene approaches on top and the dienophile approaches on bottom. Could it be the other way? Yeah. And it is about half the time. We get our product as a racemic mixture of enantiomers, some where the diene's on top, some where the dienophile's on top. We draw it with the diene on top by convention. There are 2 pieces that we need to look at for the stereochemistry of this reaction, with respect to the diene and with respect to the dienophile. The stereochemistry is a little bit easier to see with respect to the dienophile, so let's start there. Let's just add some substituents to this dienophile. We'll just make it 2 methyl groups for fun. When we draw those 2 methyl groups on the dienophile in our perspective drawing, they are going to be tucked underneath the diene. That's called the endo rule. I have a whole video about endo rule that I'll link to down below. Given that the methyl groups are stuck underneath the diene, in our perspective drawing of that instant after the bonds formed, they are still going to be pointing underneath the ring of this molecule. Now we can see how the perspective drawing is going to help us figure out the stereochemistry of our Diels-Alder product. If the dienophile is underneath the diene, and if the endo rule says that substituent is pointed underneath the diene, when that unfolds, that substituent is going to be pointed down into the southern hemisphere of this molecule on a dash. That's very important. As it unfolds, that substituent will be pointed on a dash below the ring of the cyclohexene. So we can draw those methyl groups in on dashes. Of course, the opposite holds true for the exo substituents. They would be hydrogens here. They will be pointed out away from the diene. So when it folds out, it will fold up onto a wedge if you have any exo substituents in your molecule. One other thing to point out here, we started with a cis alkene and the 2 methyl groups ended up cis in the product. This is true. The stereochemistry stereochemistry of the alkene is conserved in the product. Because it is a concerted reaction, there's no free rotation around this bond. So if they're locked into the cis position to begin with, they'll be locked into the cis position in the final product. The same is true for trans. If we had started with a trans dienophile, then the product would have had a trans orientation of those two groups. So to summarize, we conserve the relative cis-trans orientation of the dienophile in the product, and the endo rule says that those substituents will be tucked underneath the diene in our perspective drawing for this reaction. The stereochemistry with respect to the diene is a little bit harder to understand intuitively, but let me show you some visual examples that will help it make more sense. I'm actually going to start with what is traditionally one of the more complicated examples, and that's where we have a cyclic diene. But I think the cyclic diene really shows the stereochemistry well for this reaction. If I have a cyclic diene, then I have a 1-carbon bridge bridging the two sides of the diene, and so I still have a 1-carbon bridge in this perspective drawing for my molecule. Nothing changes there. Similarly, in the perspective drawing the instant after the bonds form, nothing changes here as well. We still have that 1-carbon bridge bridging the two ends of the former diene. But now watch what happens. If that group is sticking out on this side of the molecule, when this molecule unfolds, as the bottom part folds up, it's going to have to push that bridge up in order to make room for the cyclohexene. As the molecule unfolds, that bridge group is going to have to be pushed up, which means it's going to end up being on wedges in our final product. That bridging carbon is going to be on a wedge in our final product, bridging the two carbons of the former diene. By convention then, if there are other substituents on the diene, then when the molecule unfolds in the final product, those will end up being pushed down onto dashes in our final Diels-Alder product. I struggled to come up with a good way to explain this, but I had a student a couple years back come up with a great mnemonic to help you with the stereochemistry with respect to the diene. It goes like this. If we think of the diene, the 4 carbons of the diene as kind of a cave, then 2 of these substituents are pointed into the interior of this cave, and 2 of these substituents are pointed out to the outside of the cave. So we have inner substituents versus outer substituents on our diene. And here's our mnemonic. Inners are winners, and winners get thumbs up. As silly as that is, it works. As long as you can find the inner substituents, when this molecule unfolds, these inner substituents will get pushed up onto wedges, so inners are winners, and winners get thumbs up. The outer groups end up being on the dash. They are not the inner substituents, so they don't get thumbs up, they get thumbs down, and they end up on the dash in our final product. And with these 2 pro tips, you have everything you need to know to figure out the stereochemistry of any Diels-Alder problem. All right, with that under our belt, let's go back and look at this example. Let's go ahead and draw the molecules in their perspective orientations to figure out the stereochemistry. Okay, with them drawn in their perspective orientation, we can still think about the mechanism. The diene still attacks the dienophile. The dienophile still bonds with the diene, and the double bond still shifts over. Let's draw the immediate product in that perspective orientation. With the product drawn in its perspective drawing orientation, we can use our mnemonics to figure out the stereochemistry for this product. For the dienophile, the endo rule says the substituents will be pointed underneath the diene, so in our perspective drawing, when we unfold that molecule, those endo substituents will be down on dashes, and therefore the 2 methyl groups will be up on wedges. For the diene, the chlorine and the methyl group are the inner substituents. Inners are winners, and winners gets thumbs up, so when this unfolds itself, the chlorine and the methyl group will be on wedges above the plane of the new cyclohexene. And therefore the outer substituents will be on dashes in our final product. This is the product where the diene is on top, the dienophile is on bottom. It could have been the other way around, so we end up with this product plus its enantiomer. And that's it. With these simple pro tips, you too can become a Diels-Alder stereochemistry ninja.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.